Good afternoon. Welcome to the Samvaad-Talk for this week. I'm glad to introduce Professor Vittal Prabhu, who's visiting our institute as a Fulbright scholar. He's going to be here until about August of this year, May of this year. So he's been traveling to other IITs and other research institutes in India during his sabbatical for the fellowship. But he chose to work in our institute because we thought that we shared some common research interests. And so in his own words, he chose to come on this sabbatical here because he wanted to give something back to the country where he studied. So he's a native Bangalorean, studied in UEC and so on, and then went abroad to study, and then he's continued to work there. So I'm happy to welcome Professor Prabhu.
So I left Bangalore, I don't know, 30 years ago. Actually, my dad was in a transferable job, so I have no identity geographically other than having a zip code associated with Bangalore, because that's where my parents' home is. So it's great to be back. Thanks to Sachit and Professor Sadgopan for hosting me here. This part of Bangalore didn't exist when I grew up here. We could walk Bangalore, really. So I'll share with you some of the work that we have done. And I've broken this presentation into roughly 3 parts. First part is to give you some sense of why we do these crazy things. At least there are 2 controls people here, so I won't be the only crazy guy. And the second part will be a little paced tutorial. So for the students who are in here, they might actually be able to walk through this with me. And the papers that we have in the references are hopefully then become more accessible to the students. The third part is a new initiative that we are getting into at Penn State. I'll share that very briefly with you. Lots of fun opportunity there for engineers of all shades to contribute to. I'll share some of the things that we are doing in that space. So at any point you feel like, please interrupt, stop and ask question in the true spirit of Samvaad. So one of the things that we are seeing happening is our world is going to get smarter before we know, much smarter than we can actually perceive it now. I may be among the 80th percentile or 90th percentile in terms of age in this room. So I grew up in an era when internet browsers didn't exist. We were among the first few hundred who downloaded the browser that came out of USC, Urbana-Champaign. And email was unheard of. Only if you take a ComSci course, you used to get an email account. So that's unbelievable now, and it hasn't been that long. So the way our societies are going to change when we have sensing and networking ubiquitously in our world is going to be very different than what we can see right now. The other technology that is really enabling this, in my opinion, is cloud computing. I don't do any research on cloud computing. I'm just a consumer of it. I'm a very happy consumer of it because I don't have to deal with our IT administrator to access it. Okay, and that's opening up very interesting capabilities in terms of how easily I can access very powerful computing resources without having to sweat much to access it. So there are lots of opportunities here for developing a variety of algorithms, almost of every type of decision you can conceive. And what I will focus on is how we can exploit these technologies, both sensing and cloud computing, to make higher fidelity decisions, and to do so using a class of parallel/distributed algorithms. That's really the agenda for what I'm going to be talking about. And feel free to interrupt and ask questions as we go along. So in this context, we'll present a methodology for controlling discrete event systems. Okay, and in particular, we'll see how we can control the timing of discrete event systems, and we'll generalize this to other decisions that are not necessarily exclusively timing. And much of this was motivated by the schooling that I got. I was primarily schooled as an instrumentation person, not in UVC, but SIT Tumkur. about 40 miles, 70 kilometers from here. And then I went on to study in manufacturing systems and mechanical engineering. The only thing that has been common throughout my professional life is I'm a feedback controls person. That's what has colored my thought and professional life. So what we will do is we will tackle these discrete event systems decision-making problem by formulating that as a continuous variable control problem. What this does is lets us tackle these, model these as feedback control problems that you see in your HVAC control of your room temperature, cruise control in your car, whatnot. All of a sudden now we have a powerful set of tools that have been brought to us by control systems of physical systems, such as what would typically be studied in mechanical or aerospace or chemical engineering. So why should anybody care about it besides it being of an academic curiosity? Well, one reason is the problems that we are tackling are known to be among the hardest, computationally the hardest class of problems. Okay? And we can attack them using this continuous variable feedback control approach to come up with much more scalable parallel distributed algorithms. The solution quality is heuristic in the sense we cannot guarantee optimality because these are very hard problems. But what we can guarantee is the convergence rate. And I'll elaborate a little bit more about this as we go along. So the types of problems that has motivated our work is essentially out of manufacturing. Okay? Things like just-in-time production scheduling, maintenance scheduling, inventory control, transportation, supply chains, distribution, and such in this context. And this is a fairly rich array of problems that are buried in that one paragraph itself. So just to give you a big picture of how this approach can be engineered today, think of a factory here and some cloud platform up here. What we envision doing is to have this factory replicated up in the cloud and construct a cyber twin or its simulation equivalent of the factory up running in the cloud. So this enables to do a few things. Let's say the factory events run, maybe an interesting event occurs roughly every 5 minutes or every 10 minutes. You can simulate that in the cloud tens of thousands of times faster and look ahead in time. Okay? I'm talking in the factory context, but you can think of any other context that you want. You can think of transportation network, whole bunch of delivery folks traveling back and forth around the city. So you can simulate that up here if you know the current traffic conditions. So whatever be the physical system here, what we would do is we would sense the state of that physical system and send it up in the cloud. Now I'm showing this as one arrow, but it need not be one channel. It could be a whole host of sensors or other communication mechanisms that you use to send up the state into its cyber twin up in the cloud. What you would do there is play with decisions, and these decisions will be made very autonomously in a very distributed way. And then when you find good results, you ship those results back down to execute them in real time from the virtual system into the physical system. That's the overarching idea of what we would do. So the feedback control algorithm that I'm going to talk about are really running up here. And they're simply iterative algorithms that can be run very quickly in the cloud. And you get good results in, let's say, a few seconds for whatever physical system you're controlling. You can update those new decisions, better decisions to the physical system. This could be a fleet of trucks or fleet of Uber Eats folks or Swiggy folks that are hopping around Bangalore. Okay, it doesn't matter. So if we zoom in, the manufacturing system could consist of a bunch of machines, robots, whatnot. And when we started working on this problem, PCs really looked ugly like this. They were very expensive, about $5,000 US a pop. That's how much those PCs costed. But we evolved the underlying theory and mathematical machinery behind this.
So you assume that the system can be adequately modeled in the cloud.
Correct. Yes, yes. All the important features that you care to model are modelable, are sensible, and literally then you push it up.
There is non-deterministic communication in your system, like it would be in any of the industrial automation systems. Then you will have a problem duplicating that if it works, except perhaps in the sense of the characteristic of the communication. Essentially talking about packet switching, latency, traffic, all kinds of issues.
Yeah, we'll address, that's a very important and crucial issue, and whatever we design here needs to be robust enough to handle those. So to give you heads up, as long as those delays are bounded, those non-deterministic delays are bounded in terms.
I don't think this is a situation that unboundedly.
You could have a loss of communication. That's a problem. Yeah. So then you become unbounded delay. So as long as those delays result in a bounded delay of parts being processed here, then we are stable. No, I won't use the word optimality at all. I only say good results. There is no free lunch, right? I mean, we're tackling a very hard problem. Every OR person will come with a big cannon if I say optimal for this problem, right? So what we can show is, even though there are delays, which we studied actually, as long as they result in bounded delays in processing of the jobs that we are studying, then it's a guarantee to be a stable system. Okay? So what we do is, anything that is of interest to the granularity that you want to model ought to be sensed and updated into this virtual system. That's a requirement. Now, that was not possible a few years back, but now it's not only feasible but also affordable to quite some extent. And if we estimate the cost of an Amazon cloud simulation of a large factory, it costs few cents, fraction of a few cents actually. So that's the first exercise I gave my students in my graduate class. They calculated, and it's a very small fraction of a cent to do one full simulation run. So what are some of the things that this buys us? Why should anybody care about it? So we can get the resulting algorithms are in particular servo control algorithms, which means what you ask the system to do can change over time. It doesn't have to be fixed. Okay, the Swiggy driver that you dispatched, you might reroute him and ask him to go pick up something else or deliver something else. So these commands that you ask to give the system can change over time. That's what we mean by servo control. Fully distributed, which means there is no central controller or no supervisor that tells this decision maker what they need to do. Yet we guarantee the quality of what they end up doing. Feedback in these simulations are obtained through fast simulation that we run through the cyber twin that I mentioned a minute ago. So what we are able to do is, by bringing the control theoretic technique here, we can predict what will be the resulting behavior of the system without a supervisor or a central controller.
it has to be all the sensor data is going through cloud.
Correct.
So it's not actually at the edge here.
It can be distributed in very many ways. We can simulate this on a single CPU. We can simulate this on a network of CPUs. You can map each decision maker to one CPU and have them on the network. Simulation can also be distributed. So that's where the network delays come in. Starting with what I would consider one of the first distributed computing paper by Leslie Lamport. You cannot synchronize clocks. So given that as a reality, how do you engineer this system? So we won't fight that. We have to engineer around it.
Yeah, that's what I'm curious. Do you have any secret sauce around that?
Oh, and there's nothing, it's all published. No, the secret is really in this one. Okay. So when we first started working in this, esteemed reviewers, I shall not rate, I don't know the reviewers, these are anonymous reviewers from National Science Foundation, would literally laugh back at us in their writing. How can you have a system without a supervisor? It will not work. I've seen this written feedback. Okay, so we started out first building the system, showing that it actually works in real networks with ugly Ethernet, non-deterministic and everything, that it works. Now here is where any optimization people are around, I'd like to grab their attention. So for this hard optimization problem, this heuristic has provably exponential convergence rate. Now where it converges to is not necessarily the optimum. I cannot say what is the solution quality from the original objective, but I know whatever it finds, it will find exponentially quickly. So what makes this very attractive for is real-time control. If you plan well using your OR optimization solvers, let them take a weekend to crank the problem out. You deploy that solution, as uncertainties crop up in real life, you can use this as a complementary way to make good decisions and keep the performance reasonably well. Oh, no, we can only show that empirically. We can benchmark and show empirically. No, that's an open question. It is, I think, it is like a simplex problem. Simplex solves problems in polynomial time empirically, but nobody has been able to prove that, because they can always come up with a counter example where they make it nasty enough. So that is linear program. If you take a harder objective function and a harder problem, any mixed integer linear program, even small changes in the parameter values, everything else being the same, can take arbitrarily longer time to solve otherwise what seems to be the same problem. So there the solution, when it solves, is guaranteed to be optimal, but you do not know how long it's going to take to solve it. The converse is true here. I don't know how good the solution quality is. I cannot guarantee that, but I will find that exponentially quickly.
Exponential convergence and totally stable in grammar sense. We are talking essentially about the numerical part. When you go to the cloud.
Exactly. Yeah.
So you are saying that essentially it's numerically stable.
Yeah.
And it is stable in grammar sense.
Yeah. So I don't need to worry about how I initialize it or anything like that.
And so it can be implemented.
Yes.
That's what you.
Yeah.
And that of course depends upon, I suppose, you have the actual system and the work system, and the relationship between the two systems is the time.
Repeat that last part.
This system is very slow, so I can send the data there, you can make computations and implement.
Right.
The system is still slow, so that system is very fast, so it will make the situation
Sure.
and then treat it, and it can be implemented.
Correct.
That's what you're doing. The question is, of course, how far should that system be compared to the speed of this system?
Yeah. So we've studied that problem. Yeah, we studied that, and we can engineer those with today's technologies. So we built computer system performance models and tried different computing architectures and shown how fast we can scale up different types of simulation.
So essentially what I'm saying is, if it is adequate, or is my computing machinery not satisfactory?
So most commodity, we've done it with commodity PC net clusters, so we can do it.
This is empty.
Yeah. Sorry?
The duality gap gives some idea about the quality of the upper bound or lower bound between one maximum. So what I am seeing here is that we are not actually measuring the quality, but we are measuring the convergence of this.
Exactly. Exactly. We're in a very, almost looking at it in the other way. So I wouldn't talk anything about optimality, but I'll show you some graphics that will illustrate this point fairly quickly. From a computation point of view, what happens in my cloud, if I parallelize it, distribute it, it depends on what computing architecture I pick for it, is polynomial time complexity of order n square, because my simulations for these applications is really an insert sort. Worst case n squared, okay? So it's insert sort, average complexity is order n. Worst case n squared. So this is what we can think of from how long it's going to take to solve a problem. Okay? Sachit, you're going to keep me on track, right? So, any questions before we get into one fairly detailed numerical example to provide a sanity check? Okay, all right. So think of a classic decision-making problem. You have one resource, I'll call that one machine, and there are n jobs or n parts that are waiting to be processed on the machine. So the way we were trained or schooled to think is, the machine now has to pick from among these n parts. Which one will it pick next time it becomes free? So how many possibilities are there? N factorial. So that's how we are schooled to think. Okay, now we get cleverer by the day and say, okay, instead of n factorial, we'll prune the search space, make it faster, come up with branch and bound and such, and provide faster approach to search through the space and guarantee some performance measure. Okay, that's how we have all been mostly trained to think. I want to change the problem into a different way, turn it inside out. What were the jobs of the parts doing? They were just showing up there. We assume that it's something exogenous, or it wasn't a deliberate decision, they were being dumb. Now let's dumb down the machine and make the parts smarter. The parts intentionally make a decision on when they are going to arrive at the queue for the machine. So if we have n parts and one machine, now we have n decision makers. Each part is making this decision autonomously. I'm coming to CNUT's problem. It's what happens when we go to lunch at the cafeteria. We have 800 people. More or less 800 people made an autonomous decision on when they're going to arrive at the queue, right? By experience, within 5 days or 10 days of being on campus, I know I have to be there by 12:25 because or at 1:30, right? So that's how I learned iteratively. Every day I go there. Okay, there's a big bulk job that arrives at 12:30, so I better be there just before that or just after that. The same sort of smarts we can embed in these n decision maker, but in the cloud. Okay, so whatever I'm going to be talking henceforth are all the things that we are trying out in the cloud. So what we have done is, instead of making this an n factorial combinatorial problem, we now say, well, the scheduling is using timing of events. And these parts can explicitly control the timing of the events, and they iteratively evaluate the impact of their decision. They're fully distributed. They don't know how many other parts are there or even how many other machines are there. They just show up, see what happens. If they like the performance, they'll do something slightly different next time around. So this is what we call distributed arrival time control system. Arrival time because each part is controlling its arrival time, distributed because each part is making its decision fully autonomously. Okay? Now what we found is, this is the first result that we've found, and this is an empirical result, that it is able to tackle one of the hardest objective functions, that is minimizing the mean squared due date deviation for small to medium sized problem, very close to optimal. So this is a quadratic objective, one of the hardest objective functions to tackle, and exact results are there only for very specialized problems. And this approach can now tackle it for the most general one without making any additional assumption.
Similarly, in an industrial situation, a part can have it at a wrong side and necessarily it gets wrong. But then these parts are arriving in another part where the similar kind of situation.
Sure. Yeah, absolutely. So we'll start with the simplest one resource and bunch of parts, and then we'll generalize that. Maybe not with this approach. We'll tell you why. Yeah. I'll tell you why. Its objective is to minimize, to get produced just in time. It doesn't like to be completed too early or too tardy compared to its due date. Not just to be finished before due date, but it doesn't want to be completed too early either. And there are good reasons in manufacturing systems to penalize earliness, because it is probably taking away resources from some other part. You have to inventory it. And worse, if the customer sends a change and you already finished it, you will not be able to accommodate that change. There are such reasons. So this is what each part is trying to minimize. It's the difference between its own due date and its completion time. Our overall objective for the system is to minimize the mean squared due date deviation, which means we penalize larger deviations much more than smaller deviations. Fair enough? So just to use some cartoons here. So this is my ith controller for the ith job. It has a target due date that it needs to get completed. And it looks at when it got completed in the previous simulation. It has a due date deviation as a result of that. And here we plug in a little controller that will adjust the arrival time for the next simulation. So point that I want to emphasize is each part is simply looking at its own completion time regardless of what else is happening. So this decision making becomes relatively easy. Okay? But it is not doing that in vacuum. It is in fact interacting with other parts, but it is, to keep life simple, it is ignoring that. It just shows up as appropriate queuing time, increase or decrease queuing time depending on what its relative arrival time is with respect to other parts. Okay? So it is treating all the other parts' arrival time as disturbances. It doesn't control that, so it has to live with it. It's like what happens to the other 700 students who show up at the cafeteria line. You cannot control that. You just have to change your own arrival time next time around. Okay? So one controller that we will talk about takes the difference between the due date and the completion time and just integrates it over time. Standard integral controller. Okay? Standard integral controller, it is scaled by some scalar ki for the ith controller. And I want to emphasize a couple of things. One is, this is the only computation besides the simulation that is being done. Second, if I did not have this feedback system, there isn't any other dynamics in the system. The system is one. Okay. This is the difference between a physical system like this room's temperature. Okay, where the temperature might change on its own course because of the physics of the problem. Here, because this is a discrete event system, there are no underlying physics as such to add to the dynamics. All the dynamics of the system are contributed by us through the choice of the controller that we pick. Okay? So let's think of a really simple problem that you can go through this thought experiment with the aid of a graphic here. 3 parts, each one colored differently.
You work out the best way. You work out the best way things can be done in the cloud. That's where you are essentially designing the control. And then you will feed it to the actual system of implementation.
Correct. Yeah. Yes, that is correct. It's like an observer. It's like an observer that you have for missing states that you estimate. But here, it's a different scale, geographic scale.
So, essentially what you are doing is, I take the system in real time as it is, and I play with it. And then I say, from this kind of a limited horizon,
Typically a shift, 10 hours, 1 hour, something, yeah.
So, what is the best strategy? What is the best strategy?
Best decision, not just strategy, yeah. Because I'll be executing them the next instant.
I think
Correct. Yes.
I take track of things 1 hour later. the things are right. Is that always kind of open?
No, no, no. It's constantly doing that. All the time. I mean, you can always stop it if it's an economic issue, but my thought is it should be running constantly, like your control loop would be running all the time. Because what happens is when something goes wrong on the shop, in the very next simulation, it will be reflected.
I'm thinking in terms of queue formation and processing of entities in the queue and so on. And if queue logic itself gets changed, that's what is said, because of somebody else there sitting and things up. Can it really be implemented?
Sure, because the queue logic is only changing in the cloud, not in the real life.
In real life, because that's what you're saying. You work out and then you read it here. That has to be in the...
Just think about it like this. Let's suppose we had this situation of 800 people going for lunch, right? We figured out based on our calendars what is the best time for the whole institute individually to go for lunch. So when I go for lunch, there's nobody else waiting in line. They're all been served. As soon as I'm done, you are scheduled next. So we all individually, in the real system, we all experience very minimal to no queue because they all been, the uncertainties of queues has been resolved up in the cloud.
After how many iterations do you actually send it to? You have your group running.
Right.
After how many iterations do you say agent 1 or part 1 should go and...
So, okay, that's a very interesting and important question. That's why I kept harping on the conversions rate. So I know how long I need to run before I get as good a decision I can get out of the system.
That's why your explanation.
Yes. It doesn't matter. Let's confine to one queue for now. Okay, 3 parts. Neither of them know. None of them know how many other parts are there. Okay. Each one is given a due date of 10. They have different processing times. Okay, and they all want to be completed at the due date. And there is only one machine, and that machine is going to use simple policy of first come first serve. This problem is not solvable. In the sense, not all due dates can be simultaneously satisfied because there is only one machine. Okay, the parts do not know this, the machines do not know this. Okay, so let's see what happens. We give some arbitrary initial condition of 0.1, 0.2, 0.3, and machine uses first come first served. Part 1 gets processed first, and it gets completed at 1.1. Part 2 gets processed next. It gets completed at 3.1. Part 3 gets completed at 6.1. Let's say we did this in a millisecond or so. They take this completion time and we can evaluate this MSD, okay, some value, 6.88 squared. So they got this completion time. They use the integral controller to come up with the arrival times for the next iteration or the next simulation. What happens is the sequence changes because now part 3 happens to arrive earlier than part 1. Okay, the sequence that it got processed in the simulation changes. And this iteration continues. Lo and behold, the performance improved from 6.88 squared to 4.8 squared in the second iteration. You keep doing this, you can see that the arrival times change. Okay, and after about 50 or so, you can see that they converge. Now this result I got cheaply. This is the easy part. You can do this in MATLAB in 15 minutes. But what is interesting is to figure out where it converged and why it converged.
So how do I interpret this?
I'll talk about it. So that was the interesting part where Filipov came in. Okay. So what happens is, if you notice this is actually numerical noise. you see that all three parts unwittingly, we didn't know this ahead of time, have converged to the same value of arrival time, but they're hovering around that noise value there because of discretization in time. Okay, so that is some 5.87 or some mystical number there. I was thinking whether it's got something to do with pi, E or something like that. So let's figure out why it converges there, because there's nothing in this equation here, if you look at it in isolation, there is nothing here that gives me any clue about that 5.88 convergence point. Okay, so this is quite common in nonlinear systems, where you have some kind of behavior that emerges out of what would otherwise be not so apparent, but if you look at any one actor or one decision maker in isolation. So this is sort of the emergent behavior of this system, where a couple of peculiar things. One is we had fully distributed decision makers that are arriving at a consensus. Imagine everybody, Lok Sabha, Rajya Sabha had this kind of behavior. They all arrive at consensus all the time. Okay? Like, yeah. That's the service time at the machine. 1, 2, and 3. I think it was like 1, 2, and 3.
Was it that one? 1, 2, and 3. 1, 2, and
3. Yeah. So they were different.
Yeah, so the processing time for entity 1 is different from processing time. So if I randomly mix the entity,
It doesn't matter. No.
I mean,
Yeah. It doesn't matter. I'll show you the result. Why it doesn't matter. Yeah. These are good questions, and these are the questions that we grappled with too. Correct. Because preemption is too expensive in manufacturing. You can't preempt. And that's the dynamics of the system that I'll explain in a minute. Parts would, there's a soft constraint in the sense parts want to finish just in time. Yeah, they don't have much to say other than what time they'll arrive at the machine's queue.
in discrete systems, even the processing time, I can characterize. It need not be deterministic or constant.
Yeah, so here it depends on the scale of time that you're looking at. At a given instant in time, I know how healthy my machines are. I know how long it's going to take to process a part. So I will use that value.
I would specify only in terms of mean time.
That's okay.
I give a model for what kind of distribution it is. Specific age is done in discrete.
Different. The purpose is different. Okay. So it is like saying, okay, for me to go from here to MG Road, on an average it takes 58 minutes and 38 seconds. Okay, plus minus 1 hour. Okay. So that is not relevant for my trip after this talk. I need to look at Google Map and say, okay, what is the exact traffic block? How many other accidents are there? That's what is relevant for me. So that has a lot less variance. You have higher variance over longer horizon of time, right? So my horizon of time is very small.
You are not addressed that question. I mean, essentially it is a processing time which April has specified. It's a constant of each entity.
Correct.
And there are only a finite number of entities.
Yes, exactly. Yeah. Yeah. And the machine is expected to know how long it's going to take to do that particular job. That's a convenience thing. Those are for mathematical convenience. So, okay, so I'll speed up. So here's what happens when we look at the solution quality. I gave arbitrary initial condition 0.1, 0.2, 0.3. So it started out there. I forget exactly what the pink and blue curves are. I think one is MSD and the other is the average of the due date deviation. Both are like reasonable norms, they're well aligned. So you can see that it falls pretty rapidly for this toy problem with 3 parts. So it converges to within some 10-20 iterations. So here is what happens. So you look at the convergence rate, and what you say is let it run for 5 minutes or 50 seconds or whatnot. And then from among the solutions that you found, pick the one that you have the best solution and use the trace of that simulation to run the real system. Okay, so when you take the trace, that includes all the queuing times incurred, so that won't be incurred in the real time. Okay. So now let's look at how we actually analyze and predict the point where it converged to. Okay. So this was my equation. Arrival time A equals K times D minus C. So A dot looks like this. The only trick here is I can solve this under almost all conditions except when F is discontinuous. When the right hand side is discontinuous, my undergraduate calculus fails me because all the assumptions that we made was F was continuous. Yeah, Lipschitzian. Okay, so I'm going to further prune this problem to 2 parts so that I can draw it on a plane. Part 1, part 2. We have one machine. So given the processing times of P2 and P1, no part can be processed in this middle area. Okay. So if the arrival times are such that one part arrives much after the other one has been processed, it doesn't really interact with the other. They just get processed, 0 queuing time, and they go away. Okay, it's like going for breakfast very early in the morning and there is no other person waiting to have breakfast. However, if the other part is being served, then you incur some queuing time. And this depends on how long that part has been already processed while you showed up. So that is what we call the coupled region. And we can write the exact equations for this and solve the resulting differential equation using undergraduate calculus. The only time we cannot solve it is when my arrival times land on this 45-degree line when A1 is equal to A2. First come first served is meaningless, so you arbitrarily break ties. But this is the point of discontinuity where there is significant difference in performance. Infinitesimally above or below this line, the individual performance experienced by the parts are dramatically different. They're discontinuously different because the processing sequence changes. Here the processing sequence is 2, 1 below this line. Above this line is processing sequence 1, 2. It's a big change because now we have to wait for the other part to get processed. This is the underlying artifact of the system that is influencing the dynamics in a very strong way. And that is what we call the discontinuity region M, where in this case, because it is 2 parts, A1 is equal to A2 forms a discontinuity set. Now with I'll keep going on this as fast as possible. A couple of other important and interesting points. If I pick the due dates for my parts in this decoupled region, the due dates will be feasible. In the sense there will be at least one set of arrival times where both due dates can be simultaneously satisfied and both parts can be happy at the same time. If I pick anywhere in the coupled region, then they cannot be satisfied simultaneously. Okay, so there will be some penalty to be paid for it. So when the due dates are feasible, regardless of where I initialize my arrival time, the trajectory of arrival times goes and finds the good solution that is there. That's the optimal solution, guaranteed, no problem. So just to go back to what we were talking a few minutes back, if my planning system using the mixed integer linear program did a good job and came up with feasible due dates, this system can maintain it. If for some reason something goes wrong, maybe I was too far away from the mean processing time that the planner used, and my due date ends up being in the infeasible region, then it becomes some work for this controller to try and satisfy. Yeah. No, no. In fact, it is not. It is not Poisson. It is explicitly decided by the parts.
So what I'm asking is, the solution decouples the solution that you are getting from the process by which the mass is like the sense that if I had had a Poisson regular process, I could have come up with an optimal solution.
No. Even if you had deterministic arrival, even if you had a deterministic set of parts with deterministic processing times, the solution time is intractable for solving this to optimality. Forget stochastic version of it. Even the deterministic version of it is intractable. Okay. So this is the sanity check. This controller can crack this problem, so I won't waste time on it. The tricky part is when the due dates are infeasible, like the numerical example I showed. I set all the due dates to be same, impossible to be satisfied, right? So what really happens there is, when, let's look at this one segment here. So as you go along this segment, we have constant arrival time 1, but arrival time of 2 is changing along this segment. But the completion time doesn't change. Okay? That's because processing time is sequence 1, 2. So part 1 is being processed. So regardless of how much part 2 is changing its arrival time, as long as it's in that region, it's not going to be able to break free of part 1. So this is like a dead zone region for part 2. Similar dead zone region exists here for part 1. So if part 2 is being processed ahead of it, unless it is arriving much earlier or much later, it will end up facing the waiting. Okay, so this is one other nonlinearity that is there, because there is no impact on the completion time that either part sees in such case. Okay. So if I map it to the due date deviation, due date that I command them here, and this is not equal, this is off, they still see the same kind of earliness or tardiness. Okay. So if I look at this graph and say, okay, this is where I'm getting completed on this segment, and this is where I'm getting completed on the other segment, I can draw little arrows that gives me sort of a sense of the field in which the trajectory will move. Okay, so this direction is saying, okay, if I'm getting completed here, I want to really be completed there. So I draw these little lines in parallel but scaled by k that tells me the direction in which the trajectory is trying to move. And this is happening simply and explicitly because of the feedback they have. D minus C is the feedback loop that we have, scaled by k. This is telling me what direction the trajectory is aspiring to go in order to get completed just in time. So how do we tackle this one peculiarity, which is the discontinuity set? We use Philippow's approach, Russian mathematician solved this problem in early 60s, passed away recently. He generalized the entire theory of differential equations that has been developed since Newton and Leibniz, and made that a special case of his theory. So what he says is, the solution to this problem that we have, when the discontinuity has measure 0 in the space that you're working with, will be a absolutely continuous function which can be obtained using this expression, and I'll explain that in English in a moment. Now, other than the point where the system is discontinuous, you will have an exact equation which is what we call the differential equation. On the discontinuity set, you have differential inclusions, whereas on everywhere else you have differential equation, which is our undergraduate calculus is enough to solve that. So when our arrival time trajectory reaches this discontinuity point, Filipov prescribes a way to solve it. So he says your solution will belong to this uppercase f of xt given by this right hand side. What he says is, take the point where you have the discontinuity, draw a ball with delta around it, ignore this minus m means ignore the discontinuity point, because our first come first serve, for example, is not defined there. We just break ties arbitrarily. So ignore that. Anyway, it's of measure 0, so you can ignore it without impacting anything else. So you form this little ball at the discontinuity. Take the closure of the convex hull of that, okay, and you intersect it with M. This last intersection here, delta greater than 0, simply means limit as delta tends to 0 in engineering sense. Any mathematicians here? Okay, so you forgive. Sorry?
They all dabble in it.
Okay, so forgive me, but as an engineer, what this really means is take delta limit tending to 0. So you take this closure of the convex hull, intersect it with your discontinuity set, and that tells you what will happen to the trajectory once it reaches that discontinuity point x of t. Okay, so let's look at the picture. Same two-part problem. My trajectory reached this point, and here's my delta ball. There are two possible values of f there, depending on what sequence I realize, sequence 1, 2 or sequence 2, 1. Both are possible. Only two possible cases. So I get these two values of f of t. So this dashed line is my convex hull. Okay. Question is, does this intersect with this M, discontinuity set M? Now when the due dates are feasible, the problem structure is such that any resulting convex hull does not intersect with M. So what happens is, when the trajectory reaches the discontinuity line, it will immediately leave it and go on in whatever direction it chooses to go. Okay. When the due dates are feasible, which means our planning system screwed up a little bit, maybe the assumptions are not quite right, okay, then you get into this problem. This situation where the convex hull now does intersect the discontinuity line. And now that tells us how my trajectory is going to evolve from this point. Filipov gives us a nice clean solution. He says, well, you take this point x, extend it to this intersection, and this thick vector that I have, that gives me the magnitude and the direction of A dot. Okay? So that's what we saw when we initialized, and it went up to that 5.88 value. So at each point there, when the arrival times were equal, we could have applied Filipov and calculated what will be the velocity and what direction the trajectory will evolve. and it will match exactly. Okay? We have not made any assumptions to simplify the problem. We are solving the full-blown nonlinear discontinuous problem here. So what is the geometric interpretation of where it reached the convergence, the steady state value that we reach? Well, when it reaches steady state, it means A dot is equal to 0, which means the magnitude of this vector has become 0. When I solve for that, I get a very simple scalar solution. I won't elaborate this. I can take a bunch of dot products and it tells me exactly what will be the steady state value of arrival times. So starting with an ugly, otherwise ugly discontinuous differential equation, we have a scalar solution to where it's going to converge. Okay? So if the due dates are infeasible. So I can plot this graphically. Two-part problem. The vertical axis is MSD. So wherever I initialize it, it starts to converge down. Once it reaches here is when the arrival times become equal. That is a discontinuity set M, and it reaches the steady state value. So I can initialize anywhere along this and it will always converge there. So that is the numerical visualization, if you will, of global stability in this case. Okay. Questions on this? This is the last few slides were very rapid, but I can give you the tutorial papers if somebody is interested on this. So that was 2 parts. Similar things hold for 3 parts. We can still draw it. Here is a discontinuity point where A1 equals to A2 equals A3. Instead of 2 factorial, we have 3 factorial possible sequences, which means 6. So we have 6 different vertices. Instead of this line segment, now we have base of this pyramid. When that reaches D, A dot becomes 0. We can calculate similarly what the steady state value will be, and it matches that quite fine. So what this shows us is, for stylized problem, we can exactly predict what's going to happen. We don't need to do this in operation, but just to give us confidence that it's not going to do something crazy, this is what it's going to try and do. What happens when it reaches one of these discontinuity points is, it's constantly searching for new solutions. It's really a search heuristic in that infinitesimal ball. What is even more intriguing is, it can reach all n factorial solutions from there. So it is not getting stuck in a local minima in the sense that we are used to thinking. So I can reach here all 6 possible sequences in that infinitesimal ball. It's only the feedback that is directing me to try and seek better solution. Okay? So some quick and dirty benchmarks, fairly large problem, certainly large compared to manufacturing scale, 50 parts, same MSD. This is, oh, I didn't tell you how we pick the gains, right? I just said, yeah, that's another topic. But we can pick those gains very cleverly. Oh, this is the effect it has. So we first picked gains sufficiently small and equal, okay, and the solution quality looks like this. And then we picked gains proportional to the processing time. Larger the processing time, larger the gain, and such. The solution quality is dramatically better. So this is based on some rigorous mathematical analysis of the problem. And computationally it makes no difference, but the solution quality improves quite dramatically. Yeah. This is compared to simulated annealing. It's a very cheap heuristic, very democratic heuristic. Anybody can crank this out in a few minutes. So the blue line is from the distributed arrival time controller. and the red one is from simulated annealing. You can see that they're both fine comparable quality solutions, except that we can guarantee that this converges exponentially to whatever it does, and it generally does much faster. So now in each slide I'm going to generalize it very substantially. We're going to move from one machine n parts to parallel machines that are arbitrarily different in their processing rates, which means if I got lucky and went on a faster machine, I'll be completed much faster than the slowpoke machine that may be there in parallel to it. So the main consequence of that is the convex hull need not be planar on a hyperplane. It can be a full n space. So the thing that we lose in solution, qualitative solution, is that I'd lose the uniqueness, guaranteed uniqueness of the steady state arrival time. Now my steady state arrival time can be a set that I'll need to characterize, and we can characterize that even in very extreme cases. So parts were doing this. The machines are very dumbed down to just do first come first served, but they do impact production cost. We said, hey, let's try to influence how they choose from among the family of parts that are waiting. This can have a fair bit of effect on production cost as well as solution quality. So what we did was have the machine choose from among different part families using reinforcement learning. The question is, will it aid or adversely affect the overall solution quality? And the answer is affirmatively. It searches smaller space and finds better quality solution. Okay, and we can only quantify that empirically. Mm-hmm.
What does that mean? Does it mean that it has to arrive at time?
No. It is only a mathematical result, but what it does is, at that point where the arrival time was 6, it is searching for from among the n factorial sequences, the one that gives you the best solution. The trace of that is what you use to execute. Okay. All it shows is, okay, there is a fixed point, and in this particular case we can actually evaluate the fixed point too. Correct. Yeah. And here I change the Q logic based on some other much more nuanced production cost. Okay. And the control system is guaranteed to be stable for any Q logic except last come first serve. Because what happens is my negative feedback loop flips to positive. Except for that, it's guaranteed to be stable for anything else. Machines are getting smarter. Remember, that's how we started off this talk. Now machines are getting smart enough where they can monitor the condition and change the way in which they operate. So if there is a rush job, it might choose to operate at a faster rate. If it's not doing so well in terms of its own condition, then it might decide to run at a slower rate. So we can actually characterize that too in this. And we can now take the physics of the machining process or the manufacturing process or anything else that you have, couple that with the production system that we've been talking about, even throw in the maintenance system. You can have multiple such functions stacked together and you can study the dynamics, all using one system of differential equations. So in the cartoon that I just showed, this is the physics of the machining process, of the manufacturing process, this is the maintenance process, this is the production process. So every decision that you're making, whether it be changing the machine capacity or the maintenance schedule or the production schedule, you have to solve one differential equation. That's the computing cost. and the simulation. So computationally it is very cheap and tractable, so it's quite attractive for real-time decision making. The simulation that we run, I'll just mention that since somebody raised that question. You can change that to continuous time simulation also. You don't have to have distributed simulation or parallel simulation. That creates different complexity in itself and exploit it. So we can literally change just the variables of production system to logistics system and still apply this model. So I won't go into that. Suffice to say that we tackle inventory problems across supply chain. For those of you computationally interested, it has, this is the computing time characteristic that we predicted, and this is what we observed on a cluster that we had for a very large supply chain. Oops. We can use the same thing for parcel deliveries and have them dynamically reflect new orders. And it can handle similar algorithms, not much changes. We'll skip this part. So the other part that I didn't mention is you can impose another controller, you can add another controller just on energy. Let's say you're a spare part that's going to sit on the shelf for the next 2 weeks. You'd rather get processed when your electric bill is at cheapest cost than at 7 o'clock in the evening. So you can include that also and make your production system align with the smarter grid. 2 minutes? Okay. So I said I had 3 chunks of presentation. I finished 2. The third one is very light. So we are, my Penn State campus just worked its way out of, what is that, polar vortex. Even our doors wouldn't open. It was so cold. I think, yeah. The students petitioned and got 2 days off. Don't ask me what they did. But we've been around since 1855, and we keep plowing snow. Okay, every year it's nothing. It's a pretty known constant. How much do you think Penn State spends plowing snow every year? How much do we spend for snow removal on campus? Oh, just guess. Yeah, pretty close. 1.5 million a year. So we've been spending that every year, right? So it's a fairly large campus because it's a land-grant university. But this process was never engineered. So everybody did it the way it was done in the past. And there are way too many problems like this that we encounter in daily life. So somebody got really ticked off here at this end of the campus because the snow was not being removed at 8 in the morning and they had to navigate slippery sidewalks. To make a long story short, I got a call and said, hey, can you tackle this problem? I gave it to 2 very naive master students. They didn't know what they were getting into. That's why I call them naive. Okay, we like grad students like that. I said, okay, go crack this problem, and we set them loose. So now we have, for the first time, a well-engineered solution where we take what the real constraints are for that snow event in terms of what is the expected forecast, how many workers do we have today for this particular snow event, what equipment do I have. Based on that, we allocate the resources and try to minimize the time it takes to clear the campus. When we showed it to our senior leadership in Penn State, one of the things that they said is, hey, now we can tell people for the first time, at least with reasonable confidence, when a particular parking lot will be cleared, so people can decide whether they should wear high heels or sneakers or whatnot. Okay, so interesting things that are coming out of looking at labor-intensive service problems right under our nose. For those of you, I didn't say much about Penn State. I apologize for that. Sachin didn't give me enough time. Penn State's known for 2 things: not necessarily in that order. The top two things people know Penn State for in the US is engineering and football. I look at Sachin. We always lose to Ohio State. So when we have football games, we become the third largest town in the state of Pennsylvania. Otherwise, we're just 40,000 students and some faculty. So preceding a football game, we have these tailgate events. So one such event is to honor active duty and retired military folks in the US. This is championed by Walmart. They've been doing this for many years, and it's a pretty big party, really. About 10,000 military people and their family are fed. It's a big basketball arena, if you can imagine. And they said, hey, and these Walmart guys drive from all over the US to volunteer for this event. Walmart's very good with logistics and supply chain, but they don't have the Arkansas band, horsepower for this event because it's all volunteer run. They didn't know how to plan this. They came to us, and now we have engineered this, given them an Excel-based app where they can decide how much kitchen capacity they need to have, how much they need to pre-cook, what will be the expected waiting times. Again, a problem right under our nose on campus where we are applying engineering techniques to otherwise ad hoc solution type problem. That's an aerial view of a football stadium. After the tailgate, we move into the stadium. Situation is not much better, apparently. I don't go very often there. There are some 40-odd concession stands where you can go buy. I'll tell you how overpriced it is. A bottle of water is $4 and a lemonade is $5. Okay? And all the staff are volunteers from some non-profit like a local church. So the service is pretty pathetic. They're not professionals either. So what we have done here is one of our students has come up with what we call the Playbook for smart staffing. Depending on the inventory level and phase of the game and the queue length, he'll say, okay, how many people you should have cooking your hot dogs versus manning the cash registers. This was an ad hoc process, now we engineered it.
Can you admit about that is, I used to work in one of these shops during football season. And like it was a Sunday. The company actually doesn't care for the team. They jump for them. They care about how many of those buns you do.
Oh.
Like if you work in the store, from your profit, they deduct so much money if there are so many buns that have been opened from packet and asking. They don't care about the team.
So there was a whole dissertation that's going on around this to minimize the stockouts and wastage. Anyway, so the volunteers who work here get a % of the revenue. So it's in their interest to be smarter about how they staff it and better service. So hopefully by I'm in industrial engineering. So that's typically what we do. This is an ongoing project with a company that is down the street from us. We put all these sensors there right now, and we are monitoring a bunch of processes, like your TVS project. And we're learning a lot on predicting the health of those machines. So maybe in a few months, we will have improved their performance quite substantially. By 6 to 8% is what we expect. Okay, so this is where we're hoping to apply some of the algorithms that I mentioned. And so this is a new class of service-related problems that we're beginning to tackle in our initiative. So I think IIIT will find a whole bunch of them within driving distance from here. All over. So I'm here thanks to all the taxpayers from India and US, and the work here that I presented was by my students, postdocs. So thanks for your attention. Happy to entertain any comments, questions. Srinath, more coherent this time around?
So, and what is your main paradigm seems to be the control group, right? And have you tried using other paradigms like university?
I think conceptually it is a particular type of game, but I have not tried it. But the convergence point is the equivalent of some equilibrium in there.
You probably have
Yeah.
Have a hostile machine which doesn't want a part, then you can bring it.
It's serendipitous cooperation because they don't know.
Yeah, so each one is making a
Greedy decision.
interest, but
Yeah.
it's kind of
Just one comment, not only for you, we also do that from Iowa.
I think my cue to retire is if Penn State beats Michigan and Ohio on the road in the same season, then I know it's time for me to retire.
Well, thanks, Dr. Prabhu, for your thoughts.
Thank you.